right, hey y'all, Mr. Kyle, Myers Mathematics, and let's just jump into it. This is number 13 on a review for pre-calculus. I forgot what unit, but if this problem looks familiar, then awesome. Or if you have a problem from a different worksheet and it's, one of these or something similar to this, then this will probably be helpful for you. So without further ado, we will jump in. All of these numbers, well, I guess it's one number really, but it's 6 problems. All of them kind of fall under the same category. It's a little different if you were to do it in reverse. Like, let's say I took the tangent inverse of the sine of something. That's supposed to be a theta. That would be different than if I'm doing it this way. And that's just because of the order. When I'm doing the sine of an angle, it's going to make a ratio, and then the tangent inverse of that ratio would give me a certain angle. And because it's the tangent inverse, you'd have to look for the default quadrants and solve it that way. So those actually can be a little tricky in their own right. These tend to all revolve around using the Pythagorean theorem. So let's jump in and look and see what that actually looks like here. We'll start with, let's do like a lighter shade of purple here. Let's start with this one, kind of a pastel purple, and we'll kind of go through the color spectrum here, because why not? That tends to be what I do, use the primary, secondary colors to differentiate problems. Anyways, let's go ahead and jump in. So if I'm looking at what this is saying here for part A, it's the sine of an angle. Ultimately, it's the sine of an angle. Hopefully you guys can see that okay. That is a little dark. Let me try to brighten that up a little bit. Let's see if I can do this one here. Let's see if that's a little better. Yeah, that's easier to see. There we go. Okay. A brighter shade of purple here. Like a pinkish purple. So if I'm trying to find the sine of an angle, it's going to equal the opposite side over the hypotenuse side, according to SOHCAHTOA, right? Well, if I'm ultimately trying to find the sine of an angle, which is going to be a ratio, then I could say that the angle itself is this. I'm kind of doing a substitution here. So what I'm saying is that the angle itself, that's a comma, is the cosine inverse of 4/5. Making sure I'm not writing on my face here since I can't see my face when I'm looking at the screen. Cosine inverse of 4/5. And that would mean that if I take the cosine of both sides, the cosine of the cosine inverse would cancel it out. That means that I know that the cosine of some angle is 4/5. Now, this is the same angle, whatever this angle is. We don't really know. We could find out with a calculator. We could find out. We could find out what that is, and then we would know what that is. These are the same thing. It's the same theta, not two different angles, same angle. Well, whatever that angle is, the cosine of that angle is 4/5, which, remember, just like sine is opposite over hypotenuse, cosine is adjacent over hypotenuse. You guys can kind of see that. H got cut off a little bit there. That is an H. Adjacent over hypotenuse for cosine. Well, then if I were to turn this into a triangle, and this might not be to scale here. Actually, it's going to end up being surprisingly to scale, but unintentionally. So if this is the angle here, if the adjacent is 4, then the hypotenuse is 5. Well, look, that makes a right triangle, because when we're talking about basic sine, cosine, tangent, the basic trig ratios, they're set up to where they're the opposite, the adjacent, or the hypotenuse, the one of the 3 sides of a right triangle. Well, because I know 2 out of the 3 sides of a right triangle, I can use Pythagorean theorem to solve for the other one, which would be, I'm going to put a circle around this, 3, and I'm going to put a circle around it because you could use Pythagorean theorem to find it out, but it's a 3, 4, 5 triangle, so if you know a few Pythagorean triples, meaning like nice numbers that make a 3, 4, that make a right triangle, the sides of a right triangle. If you know a few of those, then you kind of just spot them over time. But if you didn't spot it right away, it's fine. You would just use Pythagorean Theorem, and you could solve for the 3 that way. It would have been opposite squared plus 4 squared equals 5 squared, and then you would solve and you'd get 3 eventually. So we found out that the opposite side is in fact 3, which means that the 3 would be in the numerator, and the hypotenuse is still 5. So that would be the answer. Okay, as we go and do B and C and the rest of these here, I'm going to start speeding up a little bit. 1, because that's what I typically do, and 2, because I'm going to definitely not have enough space unless I zoom out if I want to get all 6 of these done without having to pinch the screen or move it at all, which I might end up having to do anyways, but we'll see. We'll see. So let's go to blue, and actually I'm going to get rid of this. I think I'll get rid of this and make some space for it. All right, so B is next. So if we're looking for the cosine this time, right, then we're looking for the cosine of theta. We're looking for the cosine of theta, which means that the cotangent of theta would be 3/2. Does that make sense? So I'm kind of skipping a step here. I would know that theta then would be cotangent inverse of 3/2 because I'm substituting cotangent inverse of 3/2 for theta, which means I'm now just simplifying it down. I'm just finding the cosine of theta, but that also means that the cotangent of theta would be 3/2. And then I can put that into a triangle again. So I can make myself a little triangle here. And the cotangent is the reciprocal of tangent. Tangent is opposite over adjacent. So this is going to be adjacent over opposite. These are like way more to scale than I'm actually trying to accomplish here. Like I'm just like randomly drawing these triangles, and they're relatively to scale. So, I mean, it's a good idea to try to draw them to scale. It's not the end of the world if they're not. But it is helpful if you draw them to scale, or you try to. So then this would be 3 squared is 9. Let's go ahead and write this out, because this is not going to be a Pythagorean triple this time. So this is going to be a squared plus o squared. Oh, I wrote o squared instead of plugging in 2. A is 3, o is 2. A squared plus o squared equals h squared. 3 squared is 9. 2 squared is 4. 9 plus 4 is 13. And then I would need to take the square root. So h is going to be the square root of 13. So I'm going to put that in a circle, because that's a value that I had to solve for. And that is a 13. It kind of got embedded into the hypotenuse side of the triangle. But we now have the hypotenuse. And so then the cosine of the angle, same angle, is going to be the adjacent over the hypotenuse. This time around, we are probably going to have to rationalize the denominator. If your teacher doesn't need you to, then you can ignore this step. But a lot of teachers do, so I'm going to include this. If you rationalize the denominator, just remember to times it on the top and on the bottom. The reason why we can do that is because any number over itself is 1, so I'm essentially just timesing this fraction by 1. But that gives me 3 root 13 over 13 for my answer for B. Okay? And 13 and 3 don't have anything in common. If the fraction does simplify, you want to make sure you simplify it. So don't just rationalize and not try to simplify. Because if the fraction does simplify, then your teacher might count you off a little bit. Or maybe not, but just giving you a heads up. Okay, next one. And again, we're going to go a little bit faster as we go here. Went a little bit faster for B. We're going to go a little bit faster for C. So I can go ahead and cut to the chase here. I'm going to go ahead and just say, okay, so I know that I'm going to need a right triangle. The cosine of an angle, the cosine of the angle is going to be 3 over 4. 3 over 4, which remember is adjacent and hypotenuse. So that's going to be 3, 4. This one is also not going to be a Pythagorean triple. Cosine of theta is adjacent over hypotenuse, so that's going to be 3 squared plus the opposite squared equals 4 squared. So that's 9 plus the opposite squared. If you don't want to use O because it looks like a 0, then you're welcome to use a different letter. If you try O and then you mistake it for 0, then just use a different letter. It's not worth it. You don't have to copy everything I do. I'll let you know, like in this case, if there's something that I do that it's just a suggestion, not really like definitely do it this way because I think it's the best way to do it. So O is just because I wanted to call it the opposite side, but you could just use B since B doesn't really look like a number. If I subtract 9 on both sides, then that's going to be what, 7, right? 9 plus 7 is 16, yeah. And then I would take the square root, and I get that the opposite side is the square root of 7. Again, not a Pythagorean triple. If one of the sides of a right triangle, or more, sometimes it could be all three, I guess, if any of the sides, one or more of the sides, are irrational, then it's not considered a Pythagorean triple. I would say that some people like to say that Pythagorean triples have to be whole numbers, but I don't think they necessarily have to, because you could take a 3, 4, 5 triangle and divide each side by 3, and then you'd have another Pythagorean triple that would have some fractions in it. So it just kind of depends on how you define it, I guess. Anyways, we have that the opposite side is the square root of 7. Tangent, though, right, because we're looking for tangent. We're looking for the tangent of theta. Tangent of theta is the opposite, which we just solved for, over the adjacent. And we actually don't have to rationalize the denominator on that one, so we're done. All right, next. D. Oh, that is a little bit that's too thick. We're going to go down to 2. I make the yellow a little bit thicker sometimes because yellow doesn't contrast well with white. However, I'm mainly writing on a black background here, so it'll be fine. Okay, so sine of the cotangent inverse of -2. If it's not a fraction, you can make it a fraction. You can make anything a fraction. Just divide it by 1. And then it's a fraction. So we know then, remember, cotangent is adjacent over opposite. So we're going to just jump right into the triangle here. Adjacent 2 over opposite 1. This one is definitely not trying to scale. But it's okay. It's not the end of the world. So if we did Pythagorean theorem, that would be 2 squared is 4, plus 1 squared is 1, so 1 and 4 make 5. This would be the square root of 5. Okay, doing some quick math here. So cotangent inverse of -2. Well, now we're dealing with something that's negative. This is going to be a little bit different. So we're in, what quadrant would be? So the default quadrant for cotangent for a negative would actually be quadrant 2, since if you clip off cotangent so that it's only showing one full connected period, you would clip it from 0 to pi. And then if you flip it around to get the cotangent inverse, then you'd have it flipped on its side and it would still be a function. So the default negative quadrant for cotangent is going to be quadrant 2. Which means if we're negative here, then we're actually in quadrant 2. So I am actually going to redraw this triangle. Always be extra careful with negatives. Negatives are really that much trickier, right? Whenever you first learned about integers, combining positive and negative whole numbers, right? Like -2 minus -7 and stuff, like that got a little harder, right? We always want to be careful when we're dealing with negatives. So I am going to redraw this because this is actually in quadrant 2. Cotangent is adjacent over opposite. So it's actually going to look more like that. And now it's a little bit more drawn to scale as well. So that's helpful. This would be the square root of 5 still. because I'm still going to be, squaring the 2, squaring the 1, getting that square root of 5. So that's still going to be a square root of 5. And the radius is always positive. However, the adjacent side is negative. Now, in quadrant 2, sine is positive. So this angle, it's a quadrant 2 angle. The sine would still be positive of this. So this one is probably going to be the hardest out of all of them for anybody to get because it's got a negative in it. So just be really careful. However, what I'm trying to accomplish here is the sine of theta, which is opposite over hypotenuse, and then I would rationalize it. When you rationalize the denominator, if the numerator doesn't have any common factors with the number under the radical in the denominator, then you kind of just copy paste the denominator into the numerator, and then you just kind of remove the radical bar, the radical symbol, off of the number. That's practically what you're doing. What we're actually doing is timesing the top and the bottom by the square root of 5. But practically, if that helps to think about it that way, just like move it up to the top and then take off the, take off the hat, so to speak, then that's actually like practically kind of more like what we're doing there. So that's the answer to that one. And now we're moving on to E. Oh, and I just realized because we have 6 of them, we can use the 6 primary and secondary colors. So that's actually worked out pretty well for us. Here's orange. And let's jump into orange here. I'm going to do orange kind of off to the side underneath my face. That way I can do F right below where F is. Because that'll end up being enough space there, I think. So it looks like we're positive again. And the reason why up until D I didn't really worry about the quadrant is because everything is positive in quadrant 1. So if it's positive, we just assume we're in quadrant 1. The default positive quadrant is quadrant 1 for everything. So if it's positive, it's way nicer than if it's negative. Nothing has a default quadrant of 3 for a negative. It's just how it is. Everything either has a default negative quadrant of quadrant 4 or quadrant 2. It just depends on what the graph looks like and where it's connected and stuff. So it is what it is. If the teacher's using different default negative quadrants, that is slightly possible. There's mostly a consensus on which quadrants are supposed to be the negative ones. But if you're not absolutely sure, I would just make sure like you get a list of those from the teacher. Make sure that he or she is like letting you know which ones are the default quadrants that they're going to be using. But typically it has to do with what the graphs look like. I won't jump too much into that here because just I want to try to keep the video short. And I tend to be talkative enough as it is. So let's go ahead and round off these last 2 problems. We are looking for the tangent inverse of the square root of 3 over 4. So that's going to be tangent. That's going to be the opposite. So the opposite is the square root of 3. And the adjacent is 4. We're in quadrant 1 again, so that's nice. Square root of 3 is about 1.7. So this is going to be maybe like yay, more or less. We got this and this. And the square of 4 would be 16. The square of the square root of 3 would be 3. 16 plus 3 is 19. And that doesn't have a square root, so that's kind of annoying, but it is what it is. So we get that. 16 plus 3. Weird. Normally it's only ever one side that has a square root, but hey, I think it's possible to have all 3 sides be the square root. They typically don't give you all 3 sides as a square root, but even this is a little unusual. Anyway, sorry I'm getting a little long-winded. We're rounding it off here. Gotta finish strong, guys. So we are wanting the cosine of the angle, which is adjacent over hypotenuse. We're going to have to rationalize this one as well. Adjacent is 4. Hypotenuse is square root of 19. So that's going to be 4 root 19 over 19 because 19 is a fairly large prime. Doesn't have any common factors with 4. So there we go. All right, last but not least, here we go. Red. we have that the tangent inverse is 2 root 3 over 3. Now we could actually like unrationalize that, as in we could rationalize the numerator, and that would clean that up a little bit, but I'm not going to do that because I feel like that's not really necessary. So we're just going to leave it as is, actually. And this one is positive, so we're in the default positive quadrant, aka quadrant 1. So I did say I was going to put this underneath, but I'm not going to put it right underneath because I need the work to be kind of off to the side. It's not my greatest right triangle ever. Tangent is opposite over adjacent. So that's going to be 3 squared is 9. 2 root 3 squared, so the whole thing squared, would be 2 root 3 times 2 root 3. So 2 times 2 and root 3 times root 3. 2 times 2 is 4. Root 3 times root 3 would be the same thing as root 3 squared, or you could say root 3 times root 3 is the square root of 9, which is 3. Either way, you get 3. So it's 4 times 3, which is 12. So I got 12 for that. Because remember, 2 root 3 squared is 2 root 3 times itself. So be really careful with that. You can either view it as being times by itself, or you can distribute the square. You would distribute the square and square the 2, square the square root of 3. And that's going to equal the hypotenuse squared. 9 plus 12 is 21, contrary to the meme. 9 plus 12 is 21. So we get that. And we're looking for the sine. The sine of the angle is the opposite, 2 root 3, over the hypotenuse, the square root of 21. So this one actually will simplify a little bit because 21 and 3 already simplify. In fact, if I write it like this, I could say that this is 2. And then whenever you have radicals, as long as they're the same kind of radical, if they're both square roots, you can put them all under the same one. Or you can do the opposite and split them up. 3 and 21 have a common factor of 3. So this would actually be 2 over the square root of 7, which would then be 2 root 7 over 7. So that's one way we could have done it. The other way is we could have just timesed it by the square root of 21. Can you guys see this? Yeah, you can. Okay. We could have just times the top and the bottom by the square root of 21. Like that, right? And then that would give us the 21. So that would give us, that would be what, 63, 2 root 63 over 21. And then 63 is 9 times 7, so then that would be 2 times 3 times the square root of 7 over 21. But I think this way is a little more complicated. Would you guys agree? I think that's more complicated. So yeah, I like this way better. Try to divide, reduce the fraction. If you can reduce the numbers that are outside of the radical, awesome. If you can reduce the numbers that are inside of the radical, awesome. But you cannot reduce a number outside of a radical and a number inside of a radical at the same time because they're different kinds of numbers. They don't clash well. So you have to either simplify all the radical stuff or all of the not radical stuff, and then when you rationalize, you can clean it up after that. So hopefully that's helpful. And yeah. So I hope that's been helpful. If you want to check out other stuff, there's going to be a playlist popping up somewhere that'll have other pre-calc stuff on it. If you're interested in more pre-calc stuff, I've also got some stuff on my website, myersmathematics.com. You can go check that out. The link is going to be down in the description below. Like I have a free guide on there called the 5 math mistakes everyone makes and how to avoid them. So go check that out. As well as if you need to shoot me an email, if you're interested in tutoring and you want to look at that, what that would look like, you can shoot me an email. That's down below as well. And with that, have a blessed day, y'all. Catch you in the next episode.